It's University of Texas Energy Symposium, sponsored by the Energy Institute. I'm Carrie King, Assistant Director and Research Scientist at the Energy Institute. And before I introduce today's two guest speakers, let me point out what's upcoming. Next week is a talk on battery chemistries from our own Kent Zeng, Assistant Professor in Chemical Engineering here at UT Austin. We'll then have a week off due to spring break, and then the following week, March 25th, we'll have a presentation from Adam Birchfield, who is at Texas A&M University, Assistant Professor in Electrical Engineering, and he works on electric grid dynamic simulation models and data sets, and so we'll hear about that. But today it is a pleasure to introduce two colleagues of mine, Matthew Heun and Paul Brockway. Matthew is a professor at the Department of Engineering at Calvin University in Grand Rapids, Michigan. He's also a virtual visiting research fellow at the University of Leeds, where our other speaker, Paul Brockway, is. And he's an extraordinary professor at Stellenbosch University in South Africa. Paul Brockway is associate professor in energy and economics at the Sustainability Research Institute at the University of Leeds. A little bit more background on Matt. Prior to joining the faculty at Calvin University, he worked for the Global Aerospace Corporation and NASA's Jet Propulsion Laboratory. His driving research question is, what is the relationship among energy, materials, and the economy when viewed through the lens of sustainability? He's co-authored 3 books around this idea, Framework for Sustainability Thinking, Beyond Stewardship, and also Beyond GDP. He's trying to get beyond ideas to some new ideas, which we have today, but he's also the author of dozens of journal articles and papers, and he's the recipient of Calvin's Presidential Award for Exemplary Teaching. Dr. Paul Brockway, again, is associate professor at University of Leeds. Originally a structural design engineer, he got back into academia to explore the idea of energy rebound, which we'll hear a little bit about today. And he has a new 4-year Leverhulme Trust project titled Impacts of Green Growth and Degrowth Pathways Using Societal Exergy Analysis that we'll hear a little bit about today. And this applies what we call an Exergy economics approach. So this is your chance to learn the difference between energy and exergy, to understand energy emissions and economic pathways and implications of so-called green growth and energy degrowth pathways at the country and global scale. So their talk today will be about what they have been working on for the last 7 years, the country level primary final useful database of energy flows through society. So we'll learn with these primary energy, final energy, and useful stages of energy. This covers 150 countries from 1971 to 2020. And so it's the most comprehensive data set of this type anywhere in the world. So this is why this is an important talk to learn. If you like studying energy systems and want to understand the flows and the differences amongst countries, this is a data set to use. It elucidates the underappreciated role of energy efficiency in economic growth, and this matters because a lot of the low-carbon energy transition could be about increasing energy efficiency, and we need to know what the implications of that is, such as, is it possible to decouple economic activity from energy consumption, and what is the economic impact of the energy transition? So that said, I will now stop sharing, and we will start presentation. As always, submit your questions on Zoom via question and answer. If it's a clarifying question, I'll try to interject. If it's a more far-reaching question, we'll hold them until the end. All right, Paul and Matt, take it away.
Okay, thanks very much, Carrie. I'm just sharing my screen. If I do that, and there we go. So hopefully everybody can see the screen now.
Well, that's good. Go ahead.
Perfect. Okay, so Carrie's introduced pretty much all that. He's introduced us. He's introduced our topic, country level primary final useful energy and exergy database, and how we think we can use it to improve our understanding of energy and the economy. And hopefully in our next 2 lots of 20 minutes, we'll explain a little bit more about this. So we're going to take presentation today in 3 parts. I'm going to do the setup part, the introduction, and why we went about all of this. As Carrie said, took 7 years, so there better be a pretty good reason for doing it. Matt is then going to do the construction of the database, and show some early results from the data that we've collected. Okay, so part one, the introduction part. The framing for the database need is related to the insights that we've gained from our Exergy economics research community, which we primarily used, as we'll see, to study single country level analysis. And the purpose of the database is to go global and study many countries and make that data available for everybody else. Our Exergy economics research community was formed over 10 years ago now. We had our first meeting in 2014 in Leeds, and we generally meet in person every 2 or so years and online bi-monthly to talk about the work that we're doing. So if any of you watching today are interested in joining our community, then do drop us a line and we'll see if we can get you included in future network calls. We use Exergy economics as a space where we study the primary to final to useful energy conversion chain and also understand better its linkages to economic activity. So when I mean primary final useful energy, I'm looking at this chart here where primary energy would be, an example would be a lump of coal. So that would be a primary extracted energy source, but that is then normally converted into a final energy resource. So this would be the fuel that you're buying, gasoline at a gas station, electricity. That's the fuel that you're using to put into a machine or an energy conversion device, such as a lamp, a car, heating system, that provides an energy service to you. So you're not buying the electricity, you don't consume electricity, that would be dangerous, but you want the light at the end of it. So by understanding primary to final to useful energy conversion flows on a thermodynamic basis, we're able then to understand that conversion chain and link it to economic activity. So that's essentially the framing for the space where we work. That primary final useful energy conversion chain is shown here, and its linkages through to economic activity. And I guess what I'm presenting to you today is the insights from our Exergy economics research community in 4 areas. And there are probably more to show, but with relevance to the database, I'm showing you here. Oh, hang on, just need to move a minute. My lights. My lights have just gone off. There we go. If I don't move enough. So we've got the final to useful conversion. I'm going to show you energy return on investment, number 2. So those are both in the energy space. And then linking to the economy are understanding energy's role in economic growth and energy rebound. And those are the 4 topics I'm going to show you that we've gained single country analysis and understanding from, that is then going to be broadened by the outreach to a database. But isn't this already covered in mainstream energy economics? Well, quite simply, I don't think the answer is, or the answer is no, because most energy economy models have a final energy stage and then potentially go through to the primary stage and CO2 emissions, but they have very weak linkages to economic activity, and most certainly don't go to the useful stage, so they miss out that entire stage. Typical large system models you might see might be energy-sided models like Times model, very granular in an energy system basis, but quite a coarse interaction then with economic activity. Where on the economic-sided models, CG-type based models have quite a granular economic neoclassical framing, and then quite a weak linkage into the energy space. So neither of these really take an appreciation and can show the insights of the topics I'm about to show you. So essentially, there's a space where we can inhabit that is outside of mainly mainstream research. Okay, so number 1, final to useful energy conversion. Let's have a look at this. So recapping an example, this time of a car. So primary energy, in this case is crude oil, then converted into final energy, which would be petrol or gasoline. And then it's put into a car and we move forwards. And that's the useful energy of moving the car forwards on the road. That's the road propulsion that we're gaining as an energy service. And here what we see in the red box is that only about 20% of the gasoline that's going into the car is moving the car forwards. So we have significant losses between the final and the useful stage energy systems. But if, as a community, we spend our time looking at all sorts of energy conversion devices across transport, industry, residential sectors, all sectors of the economy, looking at the machines that are consuming final energy and understanding the amount of useful stage energy that's consumed in delivering that energy service. Then, if we take the useful stage energy as our numerator, divide it by the final energy input or even the primary energy input, that gives us a thermodynamic assessment of efficiency for an entire economy. As we see here, we see time series plots for single countries of the UK, US, which are fairly flat. China's grown quite significantly. And this gave us our first insights kind of 10 or so years ago, where we were seeing significant gains in non-OECD countries that also had significant gains in economic growth, at the same time that in the OECD countries, we had slow economic growth, but slow and low gains in energy efficiency in terms of final to useful efficiency. So that was our first kind of insight that we saw kind of 10 or so years ago as we worked our way through the final to useful energy conversion space for entire economies that had not been done before. And it made us start to think a little bit more about the practical level limits to energy efficiency on a thermodynamic basis for whole economies. The second space we've worked in is looking at energy return on investment, or net energy analysis. Some of you may be familiar with that. And two stages of, I guess, of advancement in terms of as a community that we've helped to develop in this space. One is to move the fossil fuel assessment from primary stage to the final energy stage. So here the plot on the right-hand side shows the blue lines are essentially primary stage energy return on investment. So how much energy did we need to extract a barrel of oil, or energy at source in terms of oil and gas? But if we then move the energy consumed through to the refined oil and gas stage, or to electricity from fossil fuel combustion, we see lower numerator because the amount of energy left because of losses has gone down, but we see significantly more energy used for investment. So the denominator's got much larger. That means generally somewhere between 5 and 10 would be our estimate of fossil fuel-based energy return on investment, or net energy ratio for fossil fuels. And that puts it in the same ballpark as renewables, because we've always had, up until then, we've had the comparison between the fossil fuel error is really high, renewable error is really low. Those are numbers that were going into economic models, and everyone was saying how bad renewables were going to be. But this analysis kind of said, actually, they might be much more comparable than you think when you compare them at the same energy stage. The second part we did was to move forwards and look at extending to the useful stage. So here we've got primary to final to useful energy conversion, and we were able to understand what would be the equivalent energy return on investment ratio, or net energy ratio, for renewables to be comparable with fossil fuels to deliver the same energy service. So take, for example, these results here. The ones on the top are showing that for heating systems, because the renewable transition is going to have if you're switching from heat pumps instead of a natural gas-fired furnace, then what that means is you've got much higher energy efficiency. So the coefficient performance might be 300%. So 1 unit of electricity generates 300% because of the energy that you're getting from the environment. So much higher efficiencies for the renewable-based technology. That means that on a renewable ROI viewpoint, your allowable renewable ROI ratio would be much higher. So if it was 5 to 1 for a fossil fuel-based system, if you had a three times gain in efficiency from final to useful stage, then you could allow the ROI for renewables would be 3 times higher. So it would be 15 to 1 would be allowable. So suddenly the threshold for heating and cooling based systems, when they're switching to heat pumps away from natural gas powered boilers, would be much higher in terms of the allowable ROI. So again, the work that we do on the primary to final conversion chain shows a better understanding of the final to useful efficiency for economies, but also can be useful for net energy analysis as well. Okay, insight number 3. We're now linking to energy's role in economic growth. With the country level assessments we had for final to useful efficiency gains per year, we were then able to put that into an example here of an energy economy model where final to useful efficiency was integrated right into the heart of the model. So it was the useful stage energy that interacted with the rest of the economy. And that meant we were able to understand what would be the impact of efficiency if we didn't have a final to useful efficiency gain. How much lower would economic growth be? And that's what we see on the left-hand side. So the red and black is basically observed and the base fit from our econometric model solution You'd expect them to be close because we spent a long time making the model work, and you'd expect that type of base fit. If we keep efficiency the same at 1971 levels, we see much lower economic growth. We lose about a quarter of economic growth. That's the grey dotted line. So what that tells us is, if we spin it the other way, if we add that efficiency back in, about a quarter of UK economic growth over the last 50 years has been from the final to useful efficiency gains, inducing higher economic output. So quite simply put, we would have 3 factors of production instead of 2. Instead of just capital and labour in a traditional mainstream economic analysis, we would also add in final to useful efficiency as an important third factor of production, and explaining the missing total factor, or not the missing, but explaining total factor productivity, which is not assigned to capital and labour in traditional economic models. So we think this is really important insight from the work that we've done as we've taken those single country analysis of thermodynamic efficiency, primary to final to useful stage, but now we've started to try and link it and understand how efficiency gains can be an engine of economic growth, as Bob Ayres had originally supposed. And this matters because, alluding back to mainstream models, they largely ignore the role of energy. The classic solo growth model, capital labour, but even when you add in capital labour and energy in a CES production function, still has very low role for energy in economic outputs. And here we see multi-factor productivity, which is still effectively capital and labour trying to explain growth. And then the grey stuff is what the mainstream economists can't explain because they're not willing to include energy properly within their models. This is unexplained growth, which we are saying is actually related to that final to useful energy stage of conversion. And in turn, that matters because these are the types of neoclassical mainstream economic models which are then input into the integrated assessment models which produce the assessments of emissions in the future and degrowth and pathways for emissions reduction. And so if you're not including energy and economy relationships properly, you're going to have very weak linkages, and that allows you to have systems where energy can go down and economic growth can go up due to these weak connections that we have between the two. And these types of relationships that we see here, which are capital, labour and energy CS production functions and an energy cost share relationship, highlight the very weak relationship between energy and GDP modules within these models. Okay, number 4. The other side of efficiency gains is energy rebound. Because if you have high efficiency and no rebound, you'll have lots of reductions in energy, but that's not what we see and observed with the historical record. Energy rebound may explain, from the work we've done, the disconnect in energy and economy relationships. What do I mean by that? On the right-hand side is the IEA's view. There are many similar models, but the IEA's views of essentially the 3 levers to reduce CO2 emissions at a global level. Number 1, the blue wedge, is efficiency. If you have lots of energy efficiency, more efficient devices, energy should go down. That means renewables don't have to work as hard to displace fossil fuels, and everything else can be mopped up with carbon sequestration, carbon capture storage, things like that. Those are the 3 levers. The historical record of energy on the y-axis, GDP on the x-axis, shows a fairly kind of straight line between the two in terms of growth rates. Normalized, this is back to 1971, is 1, so they've grown at a factor of about 2.5 for energy and about 4 for GDP in that time period up to 2020. But the future models you can see dotted, those integrated assessment models that we just saw, are showing that they all move to the right-hand side. So GDP continues to grow as their assumption in the model, but energy slows down. So it either grows more slowly or even goes negative relative to where it was. So energy degrows, it goes lower than it was before, which would be expected due to the hypothesis on the right-hand side that more energy efficiency will reduce energy in the future. However, there's a problem. This level of absolute global energy decoupling has not occurred in the past. This is the same plot we just saw on the left-hand side, if I'd skip back. This plot on the left-hand side, if I plot it in growth rates, I see now on the right-hand side. So if final energy grew at 2% per year historically, GDP grew at 3% per year, 2 over 3% in growth rate terms is minus 1% change in energy intensity. But you can see what happens to the prospective models on the right-hand side. Straight away, there's a step change to an average of about 3% energy intensity growth rate. So As a former engineer, that is quite concerning to see. There's no transition. It happens automatically, and this is an assumption built into the model. That's because in the past, we've been sitting in a relative decoupling space. So plotting growth rate against energy and GDP, energy's grown not quite as quickly as GDP. So we sit in that relative decoupling space. But the future models that are showing lower energy demand are saying that we're going to move into where that dot is. And that hasn't happened before in the past. Why might that have happened in the models? Well, we see the coupling between energy and economic growth in the past being due to large economy-wide rebound being a plausible explanation for why that might have occurred. The graphic on the left illustrates energy rebound. So you buy a more fuel-efficient car. The bottom bit is you drive a bit further. You have lower running costs. You're happy to drive a bit further, and you're still saving money. So that's direct rebound. You're still saving money, so you spend on something else. You might buy some clothes. You might buy some food. You might go on holiday. That's indirect rebound. And then when those system changes happen at scale, you see macroeconomic changes, particularly on the producer side, and that's macroeconomic rebound. So you have these three components of energy rebound. When you add them together, you get larger economy-wide rebound, which, looking at the studies that have estimated at a whole economy-wide scale, are typically estimating rebound should be around somewhere between 60 and 70% at an economy-wide scale. So this large economy-wide rebound, we are plausibly saying exists, and this can explain, coupled with efficiency, it's like two sides of a coin, lots of efficiency gains, but lots of rebound, will explain why energy and GDP are stubbornly kind of tied together. You can't decouple them in an absolute basis where energy goes down, economic growth goes up, at least on a historical basis. When we look at the models that are looking at future energy pathways and emissions, we see little evidence for rebound, direct, some, indirect, none, and macroeconomic partially. The same for global energy models such as BP, Shell, and the IEAs. And together, this explains if you haven't got a tight connection, you haven't got these linkages between energy and economic growth to explain periods of economic growth, it also explains why you wouldn't feature rebound in these models. And that explains why ultimately they can have such fantastic rates of decoupling that energy can go down in the model, economic growth goes up. But all we're saying is this doesn't match with reality. The models are not calibrated based on past parameters, which they should be. Okay, that's a bit of a whistle-stop tour. But in summary of the need, we pitched our idea that we needed a new global database covering primary to final to useful energy that can make a step change in energy economy research. Our last 10 years has demonstrated that with country-by-country analysis, we've made some really interesting insights into energy conversion in terms of efficiency, net energy analysis, but also links to economic growth. But a country-level global database covering many countries that is available for everybody would really help the whole community worldwide, not just our Exergy economics community, but everyone, including people attending online, to help with future-facing questions about the relationships of energy and materials, decoupling, economic impacts of the energy transition. What would the step change in efficiency mean for economic impact, for example? And how can we realistically decarbonize without destroying the economy? That's the end of my pitch and now the setup. And now I'm going to hand over to Matt and stop sharing, and he'll hopefully take you over a little bit about how we went about building the database.
Great. Thanks, Paul. Can everybody hear me? Can I just double check, Paul? You can hear me okay?
Sounds good.
All right. Awesome. Thank you. Yeah. So Paul made a good case for why we would want this kind of information available for every country in the world over many years. And I'm going to then discuss how we actually made that into a reality. So I'm going to talk about constructing the database. We had several goals for the database when we started. We wanted to capture primary, final, and useful stages. We wanted to include both energy and exergy quantifications of energy. I'll talk more about that in a moment. We wanted to enable different methods of accounting for the primary equivalent of renewable electricity. We wanted to include both fossil fuels and muscle work, that is, work that humans and animals do that they inject into the economy with their labor. And we wanted to do it for as many countries as possible, from Angola to Zimbabwe. And the good news is, the IEA, the International Energy Agency, has much data upon which we can build a database. In fact, there are hundreds of energy conversion chains in an economy, and we needed a good starting point for this work, and the IEA provides that. But there are two problems, really, with the IEA's data. As far as it goes, the IEA's data is awesome, but there are sort of two problems for our needs. The first is that the data go to final stage only. And so to recount what Paul said earlier, there are primary, final, and useful stages of energy. For this simple example here, oil reserves, maybe 100 megajoules, go into an oil refinery to make petrol, and then that petrol is used in road transport. This is the kind of data that we have from the IEA, but it's missing the transformation of final energy to useful energy, which in this case would happen in gasoline light-duty vehicles, or cars as we call them. And they would make road propulsion, say, 20 megajoules. The second problem is the IEA data are energy only. Now, energy is a heat quantification of energy. I know that sounds weird, but what I mean is if you have 20 megajoules of energy, you could get 20 megajoules of heat from it, no matter what type of energy it is. But Exergy is a work quantification of energy. And work is more economically relevant than heat. Exergy also provides rational efficiencies less than 100% for the kinds of analyses that we do. So, for example, if you have a heat pump, it takes in electricity and moves heat for you. From an energy point of view, it looks like its efficiency is 300%. But the exergy of that heat is actually quite small. So from an exergy point of view, its efficiency is only 15%. And that's a help for the kind of analyses that we're doing. So we have those two problems. The IEA data is final energy only, and we need to extend it to the useful stage and convert it to Exergy. Now, Paul earlier mentioned several country-level studies, and that's what those studies did. They converted the IEA data, or final energy data, to the useful stage and to Exergy. So here's what that data, literally what that data looked like as of about 2018. Here's Benjamin War's analysis of Japan. Here's Paul Brockway's analysis of China. You can see that it's in spreadsheets. They use different assumptions for their work, differing in hopefully small ways, but different ways. And at the sort of very bare bones level, Benjamin put his years in a column and Paul put his years in rows. So if we wanted to extend this to every country in the world, we had a big task ahead of us. Not to mention the fact that with spreadsheet work like this, if you make one mistake, you'll never find it, right? So we realized that country studies have different analyses assumptions and different data formats. And there's lots of data for all countries of the world. For example, Paul's spreadsheet over there, that was the front page of it, but there were something like 8 or 10 additional tabs supporting that particular front page. So how in the world are we going to deal with all of this if we want to extend it to every country in the world for many years? Well, it turns out we're not the only people who have been thinking about data that are structured like this. In fact, there's a world out there of input-output analysis and related techniques. Now, this world goes back all the way to the 1700s. Quenet, a dashing French gentleman, was the first person, to my knowledge, that built early economic tables. And Vasily Leontiev in 1936 was the first person to apply matrix mathematics to economic analyses. And he is the father of what we know of as input-output analysis in economics. He won the Nobel Prize for that work. I want to point out that all the way through the work of Leontiev, the data are collated and kept in monetary units only. To my knowledge, the first person to think about these sort of input and output relationships through the economy to do it on a physical basis was Ayres and Knies in 1969, and they tracked flows between sectors of the economy in mass units. Clark Bullard in the 1970s did a mixed units analysis, a matrix-based mixed units input-output analysis, where the energy sector was represented in energy units, and all other sectors of the economy were represented in monetary units, and that allowed him to calculate the energy intensity of different economic sectors. Fast forward to the 2010s, and the three dashing young men there did the first Exergy input-output type analysis. And the three of us actually were all working independently. We didn't know what the others were doing, and we are the first ones to do this kind of work in energy, pure energy, and Exergy units. So we're going to rely on this kind of data, the data organizing approach from input-output analysis to do our work for this database. So we're going to use input-output data structures and analysis methods to help us here. I want to explain how we organize the data using what we call the PSUT framework and the RUV matrices. PSUT stands for Physical Supply Use Table, and RUV is the R, U, V, and Y are the names of the matrices. So here's how we assemble these matrices. We first start out with a resource matrix, a use matrix, a make matrix, and a final demand matrix. Now let's do an example. Let's say we have the example from before. Oil reserves provide 100 megajoules of crude oil to the rest of the economy. We put those oil reserves supplying 100 megajoules of crude oil in the resource matrix. Now that crude oil is used by an oil refinery, so that entry goes in the use matrix. The oil refinery makes final energy available to the economy. So we have 95 megajoules of petrol that it makes. So we put the oil refinery and 95 megajoules of petrol in the make matrix. Finally, if we're stopping at the final stage, road transport is the consumer of those 95 megajoules of petrol, and we put that in the final demand matrix. So that's, if we have the IEA's data available to us, this is a way we can organize the IEA data into matrices to help us keep organized and make sure the energy conversion chain is described completely. But we want to go to the useful stage. So here what we're going to do is we're going to introduce gasoline light-duty vehicles. They use the 95 megajoules of petrol, and they make useful energy to the tune of 20 megajoules of road propulsion. So we put gasoline LDVs and 20 megajoules of road propulsion in the make matrix. And finally, the road transport sector uses 20 megajoules of road propulsion. So in this way, we can organize all the data for these energy conversion chains and keep everything straight and have a consistent, formal structure for all of our data. Like I said, this is the PSUT framework and the RUV matrices. It turns out when data are organized in this way, it has advantages beyond organization. So if we want to extend the useful stage, we can use matrix mathematics to help us. So for example, we can form an allocation matrix, which tells us what machines all of the final energy goes into. And we can form an efficiency vector, which tells us the efficiency of all of those final to useful conversion machines. We can also form a special vector from the final demand matrix. Once we have those three pieces in place, we can calculate a new matrix to add to the U matrix, a new matrix to add to the V matrix, and a different version of the Y matrix for useful energy as the last stage. Now, these matrix operations are really helpful because the matrix math keeps track of all of our calculations for us. Similarly, when we're converting to the Exergy quantification of energy, we can form an Exergy coefficient vector, which just tells us the ratio of Exergy to energy for any energy carrier. And we can calculate 4 new matrices, a new R matrix, a new U matrix, a new V matrix, and a new Y matrix with these simple matrix calculations. And we can convert the entire energy conversion chain from energy to Exergy quantifications. In addition to that, we can do some really interesting and simplified analyses when the data are organized this way in matrices. So for example, one matrix equation can tell you the efficiency of every single energy conversion machine in the energy conversion chain. One matrix equation can do net energy analysis, which is, as Paul was talking about earlier, akin to energy return on investment. We can figure out the embodied energy of energy. We can do structural path analysis, which allows us to determine how much of the energy is captured in paths through the energy conversion chain of different lengths. And finally, we can do what-if analyses. What if we had a different final demand for energy? Well, that would be simply a different Y matrix. And you can do what we call an upstream swim using a matrix that's called the Leontief inverse, which was developed by Vasily Leontief, to do that upstream swim, and we can find out what the energy conversion chain would have needed to look like to satisfy that different final demand. The data format that we use for the database is what I like to call a magic spreadsheet, tongue-in-cheek, of course. Here's some example data that we have. First of all, we have a column of all of our countries from Angola to Zimbabwe, years, the method for quantifying the primary equivalent of renewable electricity, which energy type we have, either energy or exergy, what's the last stage. And you'll notice over on the right here, we have 4 columns, R, U, V, and Y. And those are entire matrices stuffed into one cell of the spreadsheet. So here's an R matrix, for example, and we put that entire R matrix right into one cell of this spreadsheet. This has advantages because we can calculate new matrices very quickly with one line of code for every single country, year, method, energy type, last stage in the database. So every row can get its own new matrix. So for example, here, if we wanted to calculate the W matrix, which is V transpose minus U, we have one line of code that will calculate a W matrix for every single row in this table. We've used these new technologies to develop 2 new data sets. The first one we affectionately call the short-run data set. It's the CLPFU database, country level primary final useful. And that one has energy and exergy quantifications of energy, primary final useful stages. It goes from 1960 to 2020, and it covers 155 countries and 3 rest of world regions. The WLR-PFU, the long-run database, is a world long-run primary final useful database. It has the same characterization of energy quantification and stages as the short-run database, but the long-run database goes from 1800 to 2020, and it covers the world. It doesn't have any country-specific coverage. So how do we develop that, or how do we construct those databases? Well, for the country-level primary final useful database, where we're using IEA fuels, we start with IEA data at the primary and final stages in energy quantification, and we extend to the useful stage, and we convert everything to exergy. I mentioned before, just briefly, that we also have muscle work in our database. So this is human and animal labor injecting energy into the economy. For this, we start out with data from the UN's Food and Agriculture Organization and the International Labor Organization. And we stretch that to the primary and useful stages, then convert everything to exergy. For the World Long Run PFU database, we start out with historical sources that are usually final energy. We extend to the primary and useful stages and go convert everything to exergy. And once we've done those steps, we can aggregate and calculate efficiencies everywhere. This is all executed with computational pipelines. Now, a computational pipeline is just a number of steps to execute some sort of mathematical calculation. And we use the language R, and we use the targets package to help us with this. And here's an example computational pipeline. Every circle or square in this figure represents a step in our computational pipeline. If I zoom in on it, you can see that every one of these steps has a name, and it has data that's flowing into it and a result that flows out of it. So we can track very carefully how we're going through this computational pipeline and see where, as it inevitably does, it fails and we have to fix an error and restart it. It takes about a day to complete the entire pipeline for the short-run database. So some stats about the database here. 155 countries, 3 rest of the world regions, and world and regional aggregates. Covers 60 years, 2 last stages, 2 energy quantifications, 3 ways to include muscle work or not, 46 detailed and 7 aggregate final demand sectors, 137 energy products, 85 final to useful energy conversion machines are in there. We have more than 1 million matrices in the database itself. And in the calculation pipeline, we have many millions of matrices in there. These data are available in 2 different ways. The first is that the first paper about the database that we wrote has information in a data repository. The URL or the DOI you can see down in the lower right there. And this has allocation information and Exergy information available in spreadsheet format. Second, my students and I have built a website called Mexer, the Materials and Energy Exergy Visualizer. You can go to mexer.site, create an account, and look at the data. There's a user interface that enables you to create queries, and from those queries you can plot the data and download the data. Here's an example line plot, and you can get Sankey diagrams from it as well. Now on to part 3, some initial results from the database. Here's a graph showing useful energy and Exergy stage data for the world, colored by the different types of energy carriers at the useful stage. The red ones are all heat, the blue one is cold, and you can see that the Exergy quantification of energy is a lot less than the energy quantification of energy due to the Exergy of heat being reduced. We have this information available by sector, so you can see the different sectors here: transport, commercial and public services, industry, residential, agriculture, forestry, and fishing. And from all this information, we can calculate efficiencies. So on the left, we have 155 countries, each represented by a line. The black line is the world efficiencies. The top row is primary to final, the middle row is final to useful, and the bottom row is primary to useful efficiency. On the right, we have the change rate of those efficiencies. We also have the information on efficiencies by sector of the economy. And a little sneak peek on some work that we're doing right now. We're doing some rebound analysis with this database, as Paul was hinting at earlier. And we do this by using what we call a state map. So on the horizontal axis of this graph, we have the rate of change of final to useful efficiency. And on the vertical axis, we have the rate of change of final energy. And the point is, you want to increase efficiency to reduce energy consumption, or at least that's what many of the models suggest that we can do. So if you're along this line that's labeled rebound is equal to 0, a 2% increase in efficiency will result in a 2% drop in energy consumption. If you actually save more than that, you're in a region we call hyperconservation. If you're in the green region here, you're in a partial rebound region. If you're on this horizontal line, you have 100% rebound, where you've become more efficient, but you haven't saved any energy at all. And there's another last cases where you could backfire. That is, you could become more efficient, but actually use more energy economy-wide. So with the database, we can now ask the question for the first time ever, how are we doing on this? What are the change rates of energy efficiency and energy consumption? So we can plot each year as a dot, and you can see down below an energy and an Exergy quantification of this, this rebound stuff. And you can see that every single year that we have in the database from 1971 to today, to 2020, is in the backfire region. So it looks like as the world is becoming more efficient, we are not saving any more energy. That's all that I have for now. Here's a first page of references and a second page of references. It's been great to share some of our work with you, to give you a sense for why this is important, how we've built it, and the results that we're getting from it. And at this point, we'd be very happy to take any questions and feedback. Thank you.
Okay, thanks, Matt. Your cohort Paul here has been answering people's questions on Q&A, so I think
There we
everybody
go.
can see them, but if you cannot see them, then send another note that says you can't see Paul's results. There's one question that he hasn't answered yet, so we'll ask that one. Can you go more into depth about how to use energy to exergy coefficient to use stage matrices for net energy analysis? I don't know, maybe a lot, but is there some way you can summarize some insights from energy to exergy and net energy analysis in the work you've shown?
To move from energy to exergy, we create a vector of exergy to energy ratios and multiply that into the matrices. So that process is pretty simple. The source of the exergy to energy ratios, the phi vector, is some well-known mathematics and data that's been around for several decades. So that's not very mysterious. And then we actually track to actually do the EROI calculation. It's a little bit more complicated than what I showed earlier with the 4 matrices. We actually keep two versions of the use matrix. One is what we call the feedstock use matrix, and the second is what we call the energy industry owned use version of the U matrix. So the feedstock is basically the crude oil going into a refinery, and the energy industry owned use matrix is all of the diesel and electricity that's required to run the oil refinery. And it's the ratio of the output to the energy that is used to run the refinery that gives us our EROI. So that's how we do it. We have all that information kept categorized differently in the database, and we can essentially use matrix math to invert and divide out the inputs relative to the outputs of the energy producing sectors. That's technically how we do it. Paul, maybe you want to add to it?
Yeah, only just to sort of add maybe a different dimension in terms of, so the primary and final stage, the difference between energy and exergy is really quite small, largely because it's dominated by fossil fuels, and the exergy coefficient, it's like 1.04, 1.06 versus energy. So the plots that we see, energy versus exergy, is not much difference. The main difference is at the useful stage, essentially at the space where you're looking at heating and cooling. So high temperature heat, and so it's related to the Carnot temperature ratio in Kelvin. And so at high temperature heat, you see much higher exergy efficiencies, but low temperature heat, low temperature cooling are super low, like 5% in terms of the reduction from energy to exergy. The ratio can be really small because the temperature difference from outside to inside is only like 20 degrees. But in Kelvin, the difference is really very small. So I think that's the main difference in terms of where the exergy ratio kind of kicks in. So, but for all sorts of like transportation and most uses, anything except heat, essentially light is very similar to 1. But yeah, it's the heat uses that particularly that's where the exergy stuff becomes very different from the energy analysis.
Right. And for those who might look at the video later, Matt, I think, kind of went through that at the end and showed this useful energy final energy and final exergy versus useful energy and useful exergy consumption. And you can see, here how much lower the exergy value is.
The blue and red stuff.
I'm showing that right now.
Down.
Yeah, the blue and the reds are really get squished down over here on the right on the exergy side, whereas the pinks, which are propulsion and mechanical work, they stay roughly the same size on the right side compared to the left side.
Yep.
So hopefully that helps.
Right. So it's good that, Matt, you highlighted for people who have ever looked at the IEA data or not, that you can't just, they have such detail, you can't just add up all the energy because they're doing different things, transforming from one form to another, like oil to gasoline. So Matt and Paul and their colleagues have done all this nice hard work of organizing it so you can keep these things separate for our analysis purposes. So it's very, very handy. Go ahead.
Can I just jump back into, there was a question that Harry raised, and I've kind of partially answered it. I've directed him to like our paper, but essentially he asked a question about what happens to like emerging economies. Like, so take the example of Angola. Essentially, how did, we've done this great database, it's got 150 countries, blah, blah. It sounds too good to be true. What do we do, for something like Angola? And I think the answer to that is the IEA reports energy for all the countries, 150 plus, but then there's a whole bunch that are like rest of the world. So if they're too small or the data's too kind of patchy, they would be grouped as rest of world regions. I'm not sure if Angola is in our 150 countries, but
It is.
that broadly covers like at least 90% of energy would be covered within those 150 countries. So Angola being covered, so we would have primary and final energy, typically it might be from 1971. I don't know what year it starts, but we'd have it from the year it starts until 2020 when the current database ends. But then we go through the same process. Then we have to work out, okay, so final to useful allocation. So we've got gasoline in the road sector in Angola. Well, we use what we call as an exemplar system. So if we don't have country level data for the allocations, we basically ping it to its nearest neighbor, not necessarily geographically, but in terms of kind of economic situation, in terms of GDP per capita, or might be similar climate if it's a heating and cooling application. But basically so it might be Ghana, so we might have some good data for Ghana, so we might pin Angola in terms of its final to useful allocations from the final energy data we have at IEA to Ghana. And the same for the machine efficiency. So if we don't have efficiencies for certain machines in Angola, let's say for lighting, we would again look to say, okay, what country would be the nearest exemplar where we do have information for lighting, which may be Ghana, it might be another country. We would have basically a country that would be in its continental kind of space, and then we would spin. Eventually we have a whole set of like a world exemplars. It's like if we haven't found somebody that's nearby, it would then go further afield, and eventually we would have basically like a world average type approach for different machine efficiencies. So that's how we've done it. We've done the best that we can in kind of like 6-7 years of work between us. We have done other things, but it has been a bulk of time in the last 6-7 years. But I think Matt also explained the way that we built it was in a modular way, so that if, let's say, Harry, you've got like really good data on Angola, we can feed that in. We can improve the allocations, we can improve the machine efficiencies. So Angola then has its own data kind of feeding in. So rather than just rely on 150 Excel files with dozens of different tabs which all go wrong, we built it in a way so that we can gradually keep improving it over time, and more countries come available individually with their own data. Hopefully that's explained a little bit more about how it is, but the link I put into the answer explains a little bit more about that exemplar system.
Right. And one thing that I guess we could emphasize for those who've looked into this, IEA data are generally by pay. I think there may be the extended energy balances. I think it's roughly $1,000 if I recall. For a year, as you said, they don't calculate useful stage and they don't calculate Exergy. So via the link on the Leeds website, those data are available for free for us, but from the hard work of Paul and Matt and others. So there are certain things that are available to all of the community now from their efforts. So thank you again for that.
I think I should just clarify the IEA stuff. So we can primary final use for Exergy data, because effectively we can't release anything online which you can reverse engineer to get the IEA extended energy balance data. So we've got the primary final use for Exergy data. That's the link that Matt had on his slide. If you've got an institutional license or personal license, whatever, for the IEA data, and you can verify that with us, then effectively we can give you access to the IEA primary and final energy data because you verified with us that works. If you see what I mean. But we can't on that Mexa site, I think Matt's got a button there that talks about like energy and Exergy data. The license, the route in that Matt will then verify is if you have the IEA extended energy balance data license and you can show that to us, we can basically unlock the bit which is the primary and final energy, but we can give you the primary and final useful Exergy data, if you see what I mean, for free, because you can't reverse engineer that to get the IEA energy data. Does that make sense?
Yeah, thanks for clarifying. Let's see if we have any. Okay, thanks. That's useful. Let's see if we have another question. Any insights. So the abstract discussed, a lot of the goals to have a really good set of data to try to understand energy economy, relationships and understanding. And he talked about efficiency and rebound. I don't know, just due to your studying here, do you want to highlight insights that, I don't know, you were surprised about or that you were glad you learned about? And maybe you could even highlight the recent work you had at the end, if that was surprising to you or not. You kind of highlighted some work that's the last slide of Matt's. It's just an open question if you want to say, here's a
Yeah,
thing I learned about
Matt,
energy and
both.
efficiency.
Go ahead, Paul.
I
You
did lots of
go ahead and
talking.
start.
Matt can have a go.
Oh, you want me to go? Okay. Yeah, there's quite a few questions that we want to answer with the data. The first one that sort of popped out at us was this rebound question, because we realized that now we have a set of data that we can use to actually quantify the sort of level of rebound, if you will, in percentage terms. I didn't show it in the slides, but the anything over 100% rebound is backfire, and we've got another graph that shows that the rebound at the world level is usually between 150 and 600%, I think was the numbers, Paul. Remember that line that was bouncing around quite a bit? So I guess we suspected that there was backfire based on the previous analyses that we had done in the country level studies, but we didn't know the extent of the backfire that we would find until we actually ran the data. And that last slide that I showed is speculative in the sense that we're in the process of writing the paper for that. So we're trying to tidy some things up and hope to submit it in the next month or two, the next couple of months. But that's where we're at. And I think in terms of surprise, I guess probably surprised that it was that high. But then again, if you have an understanding, sort of biophysical understanding of the way energy in the economy works, you understand that energy is the driver for economic growth, and becoming more energy efficient can enable you, give you room to use energy more efficiently and have more money and resources available to engender economic activity. So from that point of view, it makes sense. But I think the numbers came out a little bit higher than I expected. So I don't know, Paul, you feel free to add to that a little bit.
Yeah, it's not really sort of surprised about the way we've used it, because we're building on stuff that we've done at the sort of country level stuff. So some of the insights that we saw, we're just seeing those reappear in other countries now we've got access to the data. I think for me, it's just I think we're going to start to see the benefit of creating the database, not just at a sort of personal researcher basis, because, with me and Matt, we can produce X amount of papers per year. But for me, more it's about the dissemination of this stuff more broadly through things like this type of work, online platform, but other conferences we go to, so that eventually, I know I've spent loads of time hammering the mainstream energy economy researchers, but eventually I think because of the nature of the transition, I think that's it. If we were just using fossil fuels like forever, and we did very little improvement in efficiencies, you wouldn't really see a lot from final to useful stage. We'd be spending a lot of time just finding out information that wasn't feeding back into economic growth. But because of the changes in the nature of what's happening, we're switching to renewables. That's a primary to final, like rapid change. But the final to useful change, we're switching to EVs and heat pumps. That's going to have a dramatic change on that final to useful efficiency space. And if we're right in terms of understanding the role that efficiency has in economic growth, these models, these global models that are informing energy and economic policy, are not prepared at all for what's about to happen. And so the more researchers that can start to understand that and try to get it into the modeling frameworks, I think it's only going to help future energy and economic policy be prepared for the way that the transition is going to run. So I'm excited. I'm excited to disseminate stuff. It feels a bit altruistic, but it's like, look, we sit on the outside. The mainstream community is like massive. We've got to start making inroads to them and get them to improve their models, or to get other people developing alternative models that show all the cool kind of highlights and results that we've already shown.
Excellent. All right. Any other concluding thoughts? That's maybe a good place to end there. So again, thank you. It's been Matthew Heun, Professor of Mechanical Engineering at Calvin University, and Paul Brockway, Associate Professor at the University of Leeds. Thanks for being on the UT Energy Symposium.
Thanks.
Thanks
It's been a
very
pleasure,
much.
Kerry. Thanks for the invite.
Thanks. Anybody who wants to connect with them and can't find them directly, then you can contact me. All right. Bye. Thanks, everyone.